Hello everyone, welcome to the session on algorithmic problem solving. In this session, we would like to consider the following problem. We are given a representation of a number in the decimal form and we would like to convert it to an equivalent binary representation.
The input to the problem is a number represented in decimal. The output is the equivalent representation in binary. Let us consider the decimal number 212. 212 is equal to 2 times 106. This is equal to 2 squared times 53, which in turn equals 2 squared times 52 plus 1, which is equal to 2 squared times 52 plus 2 squared, which in turn is equal to 2 cubed times 26 plus 2 squared, which equals 2 to the power of 4 times 13 plus 2 squared, which in turn equals 2 to the power of 4 times 12 plus 1 plus 2 squared, which equals 2 to the power of 4 times 12 plus 2 to the power of 4 plus 2 squared. So far, we have shown that 212 equals 2 to the power of 4 times 12 plus 2 to the power of 4 plus 2 squared, which equals 2 to the power of 5 times 6 plus 2 to the power of 4 plus 2 squared, which equals 2 to the power of 6 times 3 plus 2 to the power of 4 plus 2 squared. This equals 2 to the power of 6 times 2 plus 1 plus 2 to the power of 4 plus 2 squared. This equals 2 to the power of 6 times 2 plus 2 to the power of 6 plus 2 to the power of 4 plus 2 squared. This in turn equals 2 to the power of 7 times 1 plus 2 to the power of 6 plus 2 to the power of 4 plus 2 square. This in turn equals 2 to the power of 7 times 0 plus 1 plus 2 to the power of 6 plus 2 to the power of 4 plus 2 square. This equals 2 to the power of 7 plus 2 to the power of 6 plus 2 to the power of 4 plus 2 squared. If we now encode this in binary, we have ones in bit positions 2, 4, 6, and 7. Hence the binary equivalent of 212 is 11010100. The broad idea used in the example illustrated is as follows. Let us express n as n equals 2q plus r, where q and r are the quotient and remainder when n is divided by 2. Then r is 0 for even n and 1 for odd n. Apply this idea to the quotient again, generating a new quotient and remainder pair. These 1 remainders extract the powers of 2 in the given number. The given number is sum of the powers of 2 thus generated. Now we will try to remember these remainders on a stack. 212 equals 2 times 106 plus 0. We push 0 onto the stack. 106 is equal to 2 times 53 plus 0. We push 0 onto the stack. 53 is equal to 2 times 26 plus 1. We push 1 onto the stack. 26 is equal to 2 times 13 plus 0. We push 0 onto the stack. 13 is equal to 2 times 6 plus 1. We push 1 onto the stack. 6 is equal to 2 times 3 plus 0. We push 0 onto the stack. 3 is equal to 2 times 1 plus 1. We push 1 onto the stack. 1 is equal to 2 times 0 plus 1. We push 1 onto the stack. Now, we start popping the remainders we stored on the stack. First pop a 1. Next number popped is another 1. Next number popped is a 0. Next number popped is another 1. Next number popped is a 0. Next number popped is another 1. Next number popped is a 0. The last number popped is a 0. The binary equivalent of 212 is 11010100. Here is the algorithm pseudocode and Python code snippet for the problem. We repeatedly execute an integer division of the decimal number by 2, pushing the remainder onto the stack. Once done, we retrieve the answer from the stack by repeated popping. The algorithm runs in order log n time, where n is the number which we want to convert to binary. The space complexity is also order log n. Note that log n is also the number of bits in the binary representation of n. Thank you. This course is brought to you by Elahay Technologies.